In this lecture, we'll be talking about hashing and dimensionality reduction. For hashing, we'll finish up the conversation around locality-sensitive hashing, and then we'll talk about different kinds of dimensionality reduction. Looking back over the course, we are still in this area of implementing and analyzing standard data mining algorithms, specifically looking at dimensionality reduction. Last time, we talked about evaluating similarity in data in clusters and in other contexts. And this time, what we want to do is talk more about making these kinds of comparisons and distance calculations tractable, specifically looking at how locality-sensitive hashing works to reduce the number of pairs we have to evaluate, and then how we can reduce the overall storage costs by dimensionality reduction and address some of the issues with high-dimensional data. So in this lecture, we have three main learning objectives. The first is to finish the discussion around locality-sensitive hashing and explain how manipulating band size allows us to tune the false positive rate. Then we'll talk about dimensionality reduction and connect it back to this idea of latent factors, trying to understand what dimensionality can be doing from an intuitive perspective. And then we'll talk about two particular methods, or at least and then we'll talk about methods for dimensionality reduction. Hopefully at the end you'll be able to describe at least two of them. So first, going back to this conversation around locality-sensitive hashing, recall that when we are looking at calculating distance between a number of different elements in our data set, we want to be able to identify common or highly similar pairs. But it's difficult to identify or measure similarity amongst all pairs because this quadratic space ends up having large distance matrices that are often difficult to fit into memory. So the idea of locality-sensitive hashing allows us to address this issue by not evaluating similarity among all pairs in the in choose two style space, but only for similarity for candidate pairs, or pairs that somehow are likely to be similar. And this idea being we can specify some threshold where the similarity of any pair that we think is a candidate is likely to be above this threshold. So in our discussion of LSH last time, recall that the goal here is to find documents that are similar, at least by some threshold or above some threshold S, without having to evaluate all possible pairs. And the general idea for this was to create a function that can tell us whether two documents are similar or likely to be similar. And by scanning through the data in just a few passes, rather than having to do this for all pairs, we can hopefully reduce the amount of work we need to do by a substantial margin. So recall from our discussion about Min-Hash from last week as well, if we're looking for documents that are above some similarity threshold S, and we are constructing or have constructed our signature matrix M, where our matrix M is composed of documents as columns and rows as signature permutations from our original document matrix. Then for two documents to have some similarity of S in Jacquard similarity, that means that they have to agree on at least S fraction of the rows in the signature matrix. Now for LSH, we're going to do a similar kind of thing where anytime we have some agreement in a hashed result, we're going to leverage that as evidence that documents are similar. But we'll make a slight modification here by, rather than having to have at least some S fraction of similar values for Min-Hash, that if we ever see a collision at all. So the big idea here for locality-sensitive hashing is, given some signature matrix, we can hash the columns of this signature matrix in an intelligent way, such that similar columns are likely to end up in the same bucket, or at least result in a hash collision. So what this means is, given two candidate pairs or two documents that we think are or that have a high probability of being similar, or that are similar, then they must match in at least one bucket, or they must result in at least one hash collision when we do this hashing. So when we talked about this last week, we talked about taking our signature matrix M, we can divide it into B different bands, where each band is composed of R consecutive rows. And we hash that portion of the column, or the column associated with that band, so that number of rows, into a hash table with some large number of buckets. We want to make these number of buckets large, so when we have a collision, we can say that collision is a result of similarity within the columns, not because we have some constrained number of bucket size. And then we can evaluate or claim that any time two columns are candidate pairs, or are likely to have some threshold or some similarity above our threshold, that they will hash to the same bucket or cause a hash collision for at least one band in this signature matrix. And this allows us to tune our values of B and R to catch similar pairs without having to introduce, or somehow we tune these without introducing a significant amount of false positives. So this last part is of particular value. So remember, we can evaluate or set the number of rows in our matrix just by creating more permutations when we do our min-hash. And then once we have that number of rows in our signature matrix, we can tune B and R appropriately. So whatever value we want to set to B, we just divide the number of rows in M by B to give us the number of band, or the number of rows per band. And once we have that, we can then hash a number of these bands for these different documents into our K buckets. And then anytime we hash a new document in that particular band and it results in a collision, like these three documents at the end, we say that these three documents have collided with the other three documents that already existed in these buckets, and say that these three pairs are probably similar. They may not be. There is a possibility that they are not, but we call them candidate pairs, and they are worthy of our evaluation. Now, it's nice here because we only have to evaluate 3 different pairs, as opposed to the 7 choose 2 pairs, which is about, I think, 21 pairs that we would have to do if we did all possible pairs. And this is pretty much where we stopped last time, but we didn't really talk about how this hash collision idea is used to identify candidates and why this idea works. And the main answer here is basically about probability, and we can pin this to our min-hash implementation to talk about this. So to set this up, let's assume that we have 2 documents and they are 80% similar. And what we want to do is find pairs of documents in our set such that they are at least 80% similar as well. And we'll assume that we have some 100-element signature matrix, or some signature matrix with 100 rows. So we can set our number of bands to 20, which means our number of rows per band has to equal 5. So we have these 2 documents. We just assume that these 2 documents are average card similarity of 0.8. Because of this 0.8 similarity, they should be a candidate pair. They definitely have this higher than, or the similarity higher than some threshold. So because of this, we want to create a construct that should hash these 2 documents to a common bucket at least one time, should result in at least one hash collision. So visually what this should look like is, at some point in this signature matrix, there exists some band where for document 1, it hashes to this bucket, and for document 2, it also hashes to this bucket. And the fact that they hash to a common bucket tells us, or is indicative of a high likelihood that these 2 documents are similar. And we can walk through the math that shows us that if these 2 documents are 80% similar, there is a high likelihood that they will result in a hash collision at least one time. So how do we do this? Well, we ask the question, what's the probability that these 2 documents are identical in one particular band? So if they are identical in this one particular band, that means that it will result in a hash collision. So recall that we set the bands to 20 and the rows per band to 5. And we know that the similarity of the 2 documents raised to the r power tells us what the probability is of these 2 documents being identical in these 5 rows. So, the similarity, or this 0.8 times 0.8 times 0.8 times 0.8 times 0.8 times 0.8, is the likelihood that each one of these cells in these 5 rows will be the same. So here we can specify what our similarity and our r value is. So that tells us there's about a 30% chance, or 1 in 3 chance, that we'll have 5 consecutive rows where these two documents contain the same value. So we can flip that and say, well, what's the likelihood, or excuse me, what's the probability that these two documents do not have any similarity in a particular band, in one band? So then we take 1 minus what we just did. So we have 1 minus the probability that D1 and D2 are the same in these two rows. That gives us the probability of these two being different in one band, all 5 of these rows. So this is 1 minus the similarity of these two documents to the rth power. Now, for our particular case, we want to say, given some number of bands, what is the probability that this will happen, that there will be no collision across all 5, or all 20 of these bands, rather. So we take 1 minus the likelihood of there being a consecutive row of 5, which tells us the likelihood of there being no match in that band. Raise that to the 20th power, so that's how many bands we have, and that tells us that there's a very small probability that we'll never see any similarity, we'll never see any overlap for these 20 bands. We can evaluate this or interpret this as being, there's a 1 over 2900 likelihood of D1 and D2 hashing to different buckets for every single one of these 20 bands. So that means, or one way we can talk about this is, for every 2900 documents we see, we will incorrectly classify only one of those documents as being, or missing that one pair of documents as being a candidate, or we will say that these two documents that in reality are similar are actually not going to be candidates. This is a false negative. Now that's pretty low, so we have a very low false negative rate, which is good. But now we want to look at the flip side. Given that two documents are dissimilar, that they shouldn't be candidate pairs, how often are we likely to see that, given the construct we have for locality-sensitive hashing? So let's set a new pair of documents, D1 and D2. Say their similarity is 0.3, so they're definitely below this threshold of 0.8 that we want. So they should not be a candidate pair, given this construct. So now we can evaluate, well, what's the likelihood, or rather, what's the probability that these two documents are identical in one particular band, that they will result in a hash collision at least one time. And we get 0.3 to the 5th power, which is the number of rows in our band. So this is relatively low, it's 0.002. We want to flip that and say, well, what's the probability that these two documents are not similar in any of the 20 bands? So we do the same thing. We do 1 minus the probability of there being similar in 5 consecutive rows, and we raise that to the 20th power. And we see that we have a pretty good likelihood, or excuse me, a pretty good probability of 0.95, 95% of the time, that there will be no hash collision among these two dissimilar documents. But that means that there is a non-negligible probability that there will be a collision, that just because these two documents are below our threshold, we still have to deal with about 5% of the time, resulting in there being a collision here. So this interpretation is 95 times out of 100, we are going to correctly ignore this pair. This pair will not be a candidate pair. So this is a true negative case. But still, 5 out of 100 times, we're going to incorrectly classify this pair as a candidate pair, meaning at the end, when we have assembled all of our candidate pairs, we'll have to check this one, even though they're actually not similar. Now this rate, 5 out of 100 times, is actually something we can control by moderating or tuning the number of bands and the number of rows per band we have. So say we have these two documents with some known similarity sigma. So we can pick any number of bands of our rows and evaluate the likelihood of there being r consecutive rows in that band that all hash to the same, or all have the same value, which means it will result in a collision. We do 1 minus that to get the probability that those two bands will not, or those two documents will not hash to the same value for that band. We can generalize this out. Probability that there's no band identical is 1 minus sigma to the r squared, or to the 1 minus sigma to the rth power. So the probability of a band being different, and this must happen for every band that we have, so we raise that quantity to the bth power. So now we have a an equation for evaluating the probability of seeing one identical band, or having one hash collision, or at least one hash collision rather. It tells us essentially the true positive rate given R, given B, and given some similarity value. So we can actually graph this out and say what we want to have happen is we want to have this very hard threshold where if we look at the similarity between two documents on the x-axis and the probability of these two documents sharing a bucket on the y-axis, we want it to be the case that if two documents are below our similarity threshold, which we'll say S here, then there is no possibility that they're going to ever share the same bucket or result in a hash collision. And if they are above this threshold, then there's a 100% chance that they will result in a hash collision. Now, if we imagine that we have a signature matrix that consists of only one row, so we have one row and one band, then this S curve ends up being this 45-degree angle where the probability of sharing a bucket is directly equal to the similarity between these two documents, since the similarity is the probability of having equal hash values here. What we can actually see is if we break down or try and figure out what the relationship is between the similarity between two documents and the probability of sharing a bucket based on our ability to tune the bands and rows, then we get this. So we have sigma to the rth power. What's the probability of all rows of a particular band being equal? 1 minus that. Well, at least one row in the band is unequal, so we get no hash collision here. And we raise this to the bth power to say, well, this has to happen for all B bands that we have. And well, we don't want that to happen for two documents that are similar. So if we have at least one band being identical, we have at least one hash collision for these two documents, we end up with this structure defining what this S-curve looks like. And as a result, when we can then tune what our R and B should be in order to give us a S-curve that fits what we want. So here in this case, say we have 50 hash functions, so we specify the number of bands being 10, so that tells us we have 5 rows per band, and we get an S-curve that looks marginally like this, so we set some similarity threshold at 0.6, and we incur some cost here, that in this green area, all of these document pairs that are in this green area are going to be considered candidate pairs, or there's a high probability they'll be candidate pairs. And all these documents in the dark blue area at the top are going to be incorrectly classified as not candidate pairs. So this green shaded area represents our false positive rate, and this dark blue shaded area is our false negative rate. And we can tune the B and R to change the shape of this S-curve. So if we increase the number of bands, which consequently decreases the number of rows per band, assuming that we have the same signature matrix M with the same number of rows, then increasing the number of bands decreases the false negative rate. So we increase the likelihood of a false positive, but we decrease this false negative rate. On the flip side, if we decrease the number of bands, which is functionally equivalent to increasing the number of rows per band, and recall that means that we have a smaller probability of a hash collision given the same similarity threshold or the same similarity value. So decreasing the number of bands ends up decreasing the false positive rate. So we get fewer false positives, but we are penalized because we have a much higher rate of false negatives, candidate pairs that should have been candidate pairs because they are similar documents, but actually are not. Now, there is not one size fits all here. Picking the right S-curve or picking the right values of R, B, and the size of your signature matrix really depends on your particular context. So you can imagine the COVID-19 case where you're creating a test for whether somebody has COVID-19. You may care very heavily about the false negative rate. So it's much worse to have somebody walking around thinking that they're not infected when they actually are. Whereas the false positive rate is maybe less important, because if somebody who doesn't actually have COVID-19 is sitting in isolation in their apartment, sure, that's inconvenient, but not as bad as somebody spreading the disease more. So we can summarize this and say, well, given some data set, we can generate our signature matrix M with a particular number of rows based on how many permutation hash functions we have. We can then evaluate or set our B value for a number of bands, which then sets our number of rows per band. Because what we want to do is get many pairs that are likely to be similar while reducing the number of pairs that we have to check. But critically, we don't have to check all n squared pairs. We can scan through all of our documents and a handful of scans to populate our hash tables, and then just check the hash tables for where we have collisions, and that tells us candidate pairs that we need to check. And because of this possibility of having false positives, we then need to go through and evaluate these candidate pairs to really see, well, how many of these candidates are truly similar. And that's the high-level overview for what we do with locality-sensitive hashing for the case where we're dealing with min-hashing or Jacquard similarity. Now, this idea of locality-sensitive hashing is already something that we've seen. So recall for LSH, the objective is to evaluate similarity for candidates. We do the same thing with min-hashing. So min-hashing is itself a form of locality-sensitive hashing from the standpoint of trying to create a hashing mechanic where we don't have to check everything. Moving on to the idea of dimensionality reduction, I want to give you some intuition here for dimensionality reduction and one interpretation of what's happening here. So recall, core motivation we've talked about several times over the past few weeks is about making the web more useful by grouping content. Now we've talked somewhat about what these groups are used for and how they can be useful, but let's talk a little bit about what this idea of grouping means. So in a very high level case, when we talked about clustering, we've said that these clusters should represent similarity where two objects in the same cluster share some sort of real world relationship. Now, whether that means they're things of the same genre, people of the same political persuasion, products of the same kind of category on a shopping portal, or food from similar kinds of takeout, it's not specified what that similarity means, but these are all ways where you might group things into sets of similar kinds of items. And there can be very many different ways to group based on your particular needs. Like I said, we've seen this before with the retweet graph, where we can very clearly see two separate groups of political persuasion. We've talked about the different kinds of Jaguar, so that based on this kind of construct in the graph, we can imagine that things up in the upper left are automotive, not all about Jaguar the vehicle. There might be Lamborghini or Honda or Ford or whatever in this space, whereas here on the right, that's maybe a lot of software discussion or a lot of software products, and here in the bottom are about animals. So these clusters all represent some kind of connection among these items in our data. So in some sense, if we have some adjacency matrix that we want to use to extract some clustering, we have this potentially large matrix that is square in the number of nodes in our data set, and this mechanism of clustering, or this approach for clustering, drops the number of different features that we have, rather than all the features being all the different nodes in the graph. We can say our features can be what cluster you're part of. So now we have a new matrix that's n by c, and this number of clusters is definitionally can't be larger than n, and almost certainly going to be much smaller than n. So this is already some dimensionality reduction technique that we've employed just from clustering, going from the full adjacency matrix down to the cluster assignment matrix. If you've done natural language processing, you may have seen a similar kind of idea with topic modeling or latent Dirichlet allocation, where you have some matrix of documents and the words that appear in those documents, the shingles that appear in those documents, like we talked about last time. and we reduce that into a set of documents and topic maps or topic assignments. Which topics appear in this particular document. And again, the number of topics are generally much lower than the number of words, so we have smaller space or smaller feature space to deal with in this new construction. So in some sense, you're already familiar with the idea for dimensionality reduction, that these groups, these clusters that we're working with, capture this hidden relationship or some set of hidden relationships among items or among documents or elements in our data set. So we call these hidden relationships latent relationships or latent factors or latent features. We may not know what these latent factors are a priori, or maybe you do, depending on your particular context. But I want to walk you through an example of where this is useful. So a common question that comes up in political science is trying to infer the ideological position or political preference of an individual. And it turns out from politicians' behaviors on Twitter, you can do this very easily with the news they share, that a particular politician's choice of using the New York Times versus some other news source is actually pretty indicative of their political persuasion. And we see this is pretty common across a number of different politicians. Elizabeth Warren sharing Vox, Lisa Murkowski sharing Reuters, Cory Gardner retweeting something from The Hill, Elizabeth Warren tweeting something from Act Blue, Murkowski tweeting something from CNBC. We can actually use these domains as features when we're trying to characterize these politicians. So Elizabeth Warren, you might expect, is much more likely to share content from Vox or New York Times than she is to share content from more conservative sites like Breitbart or Fox News. Lisa Murkowski is a Republican, is much more likely to share content from Fox News. Maybe she'll share some content from Reuters, but almost certainly not likely to share content from Vox or HuffPost, generally liberal media sources. Whereas Bernie Sanders may share content from much further left-leaning or liberal sources. Now, we don't really know what exactly that says from a latent factor perspective or like a hidden feature kind of perspective, but you could imagine that if you look at some really high dimensional cloud where the dimensions are the domains that you share, that politicians who are conservative are kind of going to group together in some space, and politicians who are liberal are going to also group together in some other space. And in these two clusters, there's some cluster center, and we can project some line or draw some line between these two cluster centers. And then we can project these individuals down onto this line and end up with a essentially one-dimensional projection of their political persuasion or ideology on this one line. And there's a lot of work that's gone into this to show, based on your domain sharing, you can project into this line, and we can actually evaluate your political position relatively well. Whether you're sharing Vox, New York Times, NPR is going to make you, or is more likely to associate with somebody who's liberal, whereas if you're sharing content from Fox News or Conservative Review, you're more likely to be of a conservative persuasion. And in this case, ideology clearly is a latent factor and is intrinsically linked to a person or politician's choices about which news to share. As naturally, if you are a conservative politician, you're going to share news content that is sympathetic to or more in line with your political persuasion or your political agenda. Same if you're liberal, you're going to share content from liberal sources that's more in line with your agenda on that side. So this is some natural sort of link here between political persuasion. Now this means that you can decompose your choice of news sharing into this single dimension, or maybe some handful of dimensions that's linked with the political ideology, and you get this nice potentially summary statistic that would then be determining which domain or news source you're likely to share. So you can come up with somebody else who's shared other news domains and then say, well, where in this space are you? Which news domains are you likely to share? You can do that for recommendation or identify how close to people are based on political persuasion and a number of other things based in this lower space that makes a lot of analysis easier. Now that doesn't mean that all of these sort of latent factors are informative in the sense of they tell us exactly what's happening or they're easily interpretable. So from the standpoint of ideology, this is an easily interpretable thing, right? We can very clearly see that people who are far left on the scale are more likely to share liberal sources. People who are far right on the scale are more likely to share conservative sources. In the same way, if we look at topic models of words and documents that are shared, these topic models put words into groups, and sometimes these groups are very clear in terms of their interpretation. So we can see this topic here, which is a set of topics that have been extracted by a student of mine around COVID-19 discussions on social media across 5 different countries. And we see the topic here is about masks and hand washing and not touching your face and covering and wearing gloves. So this has, by looking at the tweets associated with this topic, we can say, well, we'll interpret this topic to be mostly about discussions around precautions. But there's no guarantee that the groups that you're identifying, or these latent groups, always make interpretable sense. Like here at this top, in this top topic, there's a number of not very clearly related words. We look at the tweets associated with them, and there's not a very clear sort of theme here. So there's no guarantee that these lower dimensional projections, or these low embeddings, or these low dimensional sort of representations capture a real world relationship that we know about. They could be artifacts of the data, so collinearities in the data, but there's some relationship here. Maybe it's not interpretable, but it may exist. But that's not the only way that you can talk about dimensionality reduction. So another thing that you might be familiar with are these ideas, is this idea of compressed files, so WinZip or zip files, or image compression like PNGs or JPEGs, or audio compression like MP4, AAC, these kinds of things. All of these are also examples of dimensionality reduction, where we have many bytes of data, or many byte representation of a particular file or image or document or snippet of sound, and we want to compress that down into fewer bytes. This is also a form of dimensionality reduction, but here you don't have necessarily some latent factor that you're trying to, or latent space you're trying to interpret. Instead, you are giving up or trying to reclaim space at the expense of noise, where we are okay losing something in our compression. We're introducing noise into our compression to get this smaller space or smaller representation. And we'll see a good example of that when we talk about SVD in a few minutes. So now let's talk about some methods where you can actually do dimensionality reduction. You should have some intuition about what dimensionality reduction may be doing, or how you can interpret this from a latent factors perspective or from a reconstruction perspective, which we'll talk about in a little bit more. So let's talk about how this is done. So we've already talked about clustering. This is one way that you can do dimensionality reduction, going from this full square matrix to this potentially thin rectangular matrix with very few clusters for many different elements. One way you've seen this is what we talked about a couple weeks ago with the Gervin-Newman clustering approach, where you iteratively remove edges ordered based on their betweenness centrality, and look for a maximal point of modularity, where modularity is the metric of a measure of goodness of your clustering, or a particular clustering. We've already talked about min-hashing. It's got dimensionality reduction here in the summary, where it compresses a set of documents that are featurized by their shingles or featurized by their words, of which you can have many, down into some much lower dimensional space based on the number of permutations that you've built into your signature matrix. So that's clearly some form of dimensionality reduction, because we claim that the rows in this signature matrix tell us something about this data, or tell us something about similarity in the input matrix, and the number of rows in our signature matrix is much, much lower than the number of rows in our input matrix. And here is actually a really good example of where these lower dimensions, the signature matrix, doesn't really capture this idea of some latent factor or some interpretable latent space like ideology or genre or product category. Instead, we're looking at trying to preserve the similarity characteristics between documents, and that's the thing that we're going for. Even if we can't necessarily say these two documents had this particular word in common, we can say something about these two documents had a similarity of X% in Jacquard similarity. So we've already talked about this idea of dimensionality reduction that we can answer with graph clustering, and we can answer for sets of or documents that are characterized by sets, or elements that are characterized by like sets of common neighbors. Do that with min-hashing. But there are other general methods for doing dimensionality reduction as well. So if we're trying to do decomposition to latent factors, we've talked about that to some degree. Another way to do this is to reduce dimensions where you want to minimize the amount of error you introduce by doing this reduction. So if we want to go back from our reduced dimensional space to the original space, have we lost some signal in doing this reduction in dimension, and can we choose some lower dimensional space that allows us to reduce this reconstruction error as much as possible? So PCA is one example of this, where you take some large feature matrix with many documents across in dimensions. So in this matrix we have x1 to xm different documents, and we have d1 to dn different features. And with PCA, what you do is you break down this feature matrix into a set of components, so principal components, where your first principal component, or the first column in this new feature matrix, represents the axis of most variance. So this is where most of your information, or most of the variation in your documents, is captured by this first principal component. You can break it down into a second principal component as well. There's slightly less variation here, but the variation in this second principal component is separate from, or not easily captured by, this first principal component. You can actually do this for n components. So if we have n different dimensions, we can have n principal components. This is ordered by the magnitude of the eigenvalues in your data, or in the decomposition of this feature matrix. And if you kept all the components here, really what you've just done is you've rotated your original data set. And with PCA, the goal is, given some data, we want to do this rotation, so then we can project data down into a dimension with the highest variance, or some set of dimensions where, by looking at the first 2, 3, 4 principal components, we've captured as much information as we could capture given any other set or any other projection into those 4 dimensions. So here we take this example with hello, we rotate this space, and then by projecting down into this singular dimension, we can see that we're still able to capture the general sort of variation among the data points, or the clusters of data points in this word, even though we've lost a lot of the height and we can't necessarily see that this data represented hello. We can see that there was good separation, or clear separation, between the letters in our data points. So PCA is one very common method for doing dimensionality reduction. The one that we'll now talk about is called singular value decomposition, which is more general approach to doing dimensionality reduction that has a nice intuitive kind of explanation or interpretation that we'll get to. So here, say we have some feature matrix. We already decided it's m different documents of each one of n different features. And with SVD, we can decompose this feature matrix into a set of 3 different matrices. This matrix U, which is the same number of rows as our original matrix, so we have 1 row per document in our feature set, or in our 1 row per document in our data set. We have R columns, where R is going to be much less than n, and we have a matrix sigma, which is R by R. It's going to be a diagonal matrix. And we have our matrix V, which is an n by R matrix that we transpose to get this projection. So now if you take the product of matrix U, sigma, and V transpose, we can recover matrix A. The idea here is we keep, one way to deal with dimensionality reduction with SVD is to keep only important components of these matrices, which we can do by construction, this matrix sigma, the diagonal values are ordered ordered in decreasing order. So S1 is going to be your highest value, and you can use those values as a signal for how important or how much variation exists in each one of these dimensions, and you can drop off unimportant components, which essentially, or set those unimportant components to 0, which essentially zeroes out these columns of U and V, which allows us to represent this data in a lower dimensional space, or fewer than R dimensions if we're looking just at matrix U, or fewer than R dimensions if we're looking just at matrix V. We'll talk about interpretations for that in a second. Or we can operate just in this projected space alone. So this is a better example is to talk about the product of matrix U and sigma together, which still results in an n by R matrix. This R value is going to be much lower than the number of dimensions in our original matrix, and then we can evaluate distance or similarity within this reduced space. So let's talk about how this works. So remember, I just showed you that for SVD we have some matrix A of m rows by n columns, and it can be reduced into these 3 different matrices. A is some input matrix. For example, now we'll talk about m documents and n words. U is what's called a set of left singular vectors of m documents and R concepts, if we're going to talk about interpretation. Sigma is our list of singular values, diagonal matrix, where all values except, or all cells except for what's on the diagonal are 0. And we say this represents the strength of each concept. And then V is this right singular, or set of right singular vectors associating terms with concepts. So U associates documents with concepts, and V associates terms with concepts. And you can think about this kind of graphically. We have this potentially tall rectangular matrix A that we can represent by 2 skinny rectangular matrices and 1 square diagonal matrix. From SVD, an important property here is that it's always possible to decompose any matrix into this set of U sigma and V transpose. And U sigma and V will be unique, given that, remember that sigma is this diagonal matrix. The values along this diagonal are going to be positive and will be sorted in decreasing order. So S1 is going to be the largest singular value in this matrix. And we can think about this, we can ground this interpretation in an example when we talk about movies or users to movies. Say this matrix A represents rows for users, and columns are movies, and cells represent ratings, or how much I liked a particular movie, or how many times I've watched a particular movie. You can replace this with any other sort of representation you want. It could be politicians and domains that they've shared, or people in the product categories or products they've purchased from Amazon. All kinds of representations here. So we'll ground this in this user to movies example. So we have this matrix A of users and the movies they've watched and how many times they've watched them. For instance, we can decompose this into U sigma and V transpose, where we say the U and V matrices capture the concepts underlying this set of movies or these set of users, where U relates users to the latent sort of genres of these movies that are interesting to them, and V represents the relationship between movies and the genres in which they're from. So we can ground this into what this actual decomposition may look like of U sigma and V transpose, and we say that this potentially this first column of U is called or represents the sci-fi concept. This middle column of U represents the romance concept, and this right column of U maybe captures some noise in variation of the data. So what this says is this first user in the first row, has a interest in the sci-fi concept of about 0.13. Maybe it's not necessarily clear how high that is, or whether that's high or low, but we can say that that's a high value for that row. So that user clearly seems to be more interested in the sci-fi concept than they are in the romance concept. This strength value, or this first value in our sigma matrix tells us how strong this sci-fi concept is, or how much variation there is in this sci-fi concept. And we can use this V matrix, or V transpose, as the movie to concept matrix in the same way that we had the user to concept matrix before. And this says, or maps, which concepts are most strongly associated with which movies. So here we can see that the movie The Matrix, Alien, and Serenity all have high scores for the sci-fi concept, which makes sense if we think about what those movies are. So we can talk about an interpretation of SVD as decomposing a data set, our A matrix, into a set of maps. So this first U matrix maps users to genres of interest, or some kind of latent concept or latent interest in the data. This V matrix maps our features, in this case movies, to what those concepts or latent features may be, so in this case genre. And the sigma matrix tells us, well, how strong or how much variation is there among the different latent factors or latent dimensions that we talked about, or that we've identified. So that's all well and good. Now we have some general way of representing a full data set as being some combination of user interests and item relationships with those interests. How does that help us for reducing dimensionality? One interpretation, or one set of reduced dimensionality data that we can work with, is this movie to genre matrix V, where now this row of matrix V tells us what the general relationships are between our features in our space, or the movies that we've rated, and the different genres that we have. So this would tell us that our first three movies are all likely to be strong, or all strong in the sci-fi concept, and the other two movies are weak in the sci-fi concept. And the second row tells us the same, that the last two movies are strong in the romance concept. Another interpretation is to look at this in terms of the combination of the spread of the strength of our different concepts, and the combination of that with the relationship between users and the different concepts. So we can take the product of U and sigma and create this new projection of users into their genre interests. So now we can take this matrix that is however many rows of users we have by 5 different movies, and project that into a space of a reduced space that's not based on movies, but based on the underlying genre of interest. So now this first user is clearly more interested in the sci-fi concept than they are in the other two concepts that we've extracted from our data. And then based on that kind of evaluation, we can compare users based on their preferences, not in the full space of movies, but in the space of their interests, or the underlying movie genre concept. And this will end up being much more useful when we look at collaborative filtering and recommendation systems, because then we can evaluate, well, if you are more similar to some other user who has a similar set of, or a similar interest in concepts, then we can start to extract, well, what movies are associated with that concept that you haven't seen, and recommend you movies based on that. Now, a question you may ask is, why does this reduction work? Why is it that we can just take one of these matrices from this decomposition and learn something of interest from the underlying data? And the answer is, the answer goes back to this idea of reconstruction error. So I talked about before, when we're talking about compression, a way to measure how good your compression scheme is, well, how well can you recover the original data? And here we're going to do the same thing. So if we assume this following decomposition that we've already seen before, we have this set of users who have rated, or can tell you how many times they've seen these different movies. You can break this down into U, sigma, and V transpose. This sigma matrix tells us the strength of these different concepts, but another way to think about that is how much variation, or which sets of dimensions are most important in our ability to reconstruct the underlying data. So if we actually just X, or completely zero out this lowest value, or this bottom right corner element in our sigma matrix, and redo this math where we take the products of these three matrices, we now get an approximation of the original matrix A, which is not quite the same as matrix A, because we've actually just zeroed out these last components of these two matrices. And if you do the math, you actually can show that the underlying or the resulting projection is still relatively close to the original data set. We can show this with one of the many norms that are out there when we talk about distance metrics that we talked about last time. One of them is called the Frobenius norm, which is really just the square root of the sum of the differences between elements in two equivalently sized matrices. And what we know, or what can be shown from the SVD construct, is by removing the lowest strength components from our sigma matrix, we're still preserving as much information as possible in those remaining dimensions. So the Frobenius norm is in some sense minimized by that selection, or the removing of that particular dimension, or the lowest singular value dimensions in that sigma matrix. So if we summarize what we have about SVD, we know that the decomposition from any given matrix is unique. We can map these, or we can claim that these matrices allow us to map users to concepts, movies to concepts, and evaluate the strength of the different concepts, or the strength of variation of the different dimensions that we're decomposing our data into. And even if we keep just the top k largest singular values in our sigma matrix and zero out everything else, we can still keep the majority of interesting structure in the data with fewer dimensions. But as always, when we talk about web scale data, we have to worry about how much time and energy does this take to actually do this computation. To compute SVD for a given matrix of n by m, we end up with something that's close to cubic in the size of the data, which is definitely problematic if we're already talking about the distance matrices from last time being quadratic is problematic. And beyond space issues, we also have structural issues. What we actually come out with is that this A matrix is maybe not that hard to store, because we assume that it's sparse. If we're talking about networks, or we're talking about documents and words, most nodes in the network aren't connected to many other nodes. Most documents don't contain a huge majority of words in our vocabulary, so this A matrix is generally sparse. And when we decompose this using SVD, our sigma matrix is going to be sparse by construction. All values that are not on the diagonal are zero by construction, but these U and V matrices are big and dense, which means that this is going to be a problem when we try and do storage. We're already talking about big and dense matrices from the distance matrices size is going to almost always end up in a memory issue when we're talking about web scale data. So the book introduces the Kerr heuristic. We know our data is going to be huge and sparse. We can keep this U matrix as small, but we can allow it to be dense instead of sparse like the sigma matrix, and we can impose some constraint that the C and R matrices, originally represented our U and V matrices, are still big, but now they can be sparse. And if they're sparse, then we can much more easily store them in memory without as many issues. And we do this by sampling on A. I'm not going to go deeply into the implementation for Kerr, but I will show you a clear example about where this problem comes up. So if you look at an existing data set from DBLP, which is this big computer science bibliography data set, it is a mapping of all the authors to conferences where they've published. So you have this big matrix where the rows represent authors and the columns are all the possible conferences, and it's going to be sparse. Generally, a single individual is not submitting and publishing in many conferences, but it still ends up being a very large data set. And if we want to do dimensionality reduction, to look at, what are the different fields in computer science, for example, we might ask, how long does it take to actually do this using SVD based or Kerr? So if we plot the relationship between accuracy and the amount of space and time taken up by SVD in its pure implementation, and the Kerr heuristic that uses sampling in its implementation, and we see that Kerr, and a version of Kerr that removes any duplicates from our data set, still maintain relative, or rather very competitive accuracy, and are significantly faster and use much less space than the full SVD kind of implementation. And you'll see we come back to this idea consistently when we talked about the implementation for SimRank, when we talked about the implementation for these other metrics where we can rely on sampling and not have to visit all possible nodes. These heuristics allow us to save a lot of space and time. And we can note that if you are using Python for your project, then Python's sklearn package already comes with a version of SVD available for you for doing dimensionality reduction. So that ends the Module 4 lecture. We've talked about the relationships between false positives and the band and row parameter selection for locality-sensitive hashing. I've tried to give you some intuition behind dimensionality reduction and what it could be doing, or one way you could interpret it in terms of latent factors. And we've talked about a few different ways you might actually do dimensionality reduction, from clustering to Min-Hash to SVD to Kerr. That'll all give you different ways of representing your data in these lower dimensions. If you have any questions, feel free to post in the discussion forum for Module 3 and 4.